Well, welcome everyone. I'm Vitaly. This is Drew, and this is hacking the Jolla. I should actually probably get the Jolla to show you what it is. But we are going to talk about an interesting phone that comes from the country of Finland, but we're going to do it in a way that should hopefully show some of the techniques we use to assess any mobile device. So hopefully there's something interesting for people that know about this stuff and people that are new to this stuff, some generic techniques you could use. Hopefully it's a good intro. Mobile phones, embedded devices, Linux hacking in general, what have you. So a quick history of what the Jolla is. So basically, Nokia at one point had the Maemo platform. It was a Linux-based OS. It was somewhat popular with a certain crowd. And eventually something's happened, and they wound up merging with Moblin Mobile Linux from Intel. This became MeeGo. And then a phone came out based on the MeeGo called the Nokia N9. And this got a cult following, and right after this happened, Nokia said, we're not going to do Linux phones anymore. We're just going to build Windows phones. And when this happened, they got rid of all their Linux phones, and a lot of the engineers left. So Nokia, they have this thing called the Bridge Fund, and they actually gave their engineers some money to start a new company. And from this, we got the Jolla, which is what we're talking about today. So, yeah, so they got funding, they got no intellectual property, right? So they took what they could to work with. Between them leaving and this happening, MeeGo got forked into an open source project called Mare, and they wound up using that. They combined open source with a bunch of technologies like Wayland. You might be familiar. It's like the replacement for Xorg. They use Qt5, QML, and they also wrote a bunch of proprietary stuff on top. Silica, which complements Qt Quick, Lipstick, which is the actual shell that you see running on the phone. And they also changed a bunch of things. If you're familiar with Maemo or MeeGo, they changed a lot of the technologies that you could see there. I don't want to spend too much time on it. So from this, we got Sailfish OS, which is the actual operating system, Linux-based operating system that's running on the Jolla phone. I want to mention this real quick. There's a really cool back cover. I'm going to grab the Jolla here in a second. A smart back cover that goes on these phones. So the idea is you pop a new cover on and you get a new theme, a new ambiance, or you could even use it as like a keyboard or whatever you want. And so obviously this kind of gets the gears turning about what does this use. And there's NFC involved, there's I2C. We're not covering it during this presentation, but if you're curious, at Echo, a little bit, but if you're curious, at Echo Party we talked about it, our co-presenter Chris Whedon, who's not here, did that research. So if you're curious, grab a slide deck. There's actually, he hooked up the pins, he tried to do a little I2C fuzzing, so there's some interesting stuff going on there. Just real quick, this is kind of an artist's rendering of the possibilities, things you might be able to do with the other half. The keyboard's already out. Anyway, we're going to get to the attack surface of the phone, and what we wanted to do is start from like, when we get a new device, what is it that we look at? What are the different attack surfaces? And before a phone can boot, the operating system, you know, some things need to happen, right? And the boot process in a phone is actually really interesting. And we thought, you know, what's the bootloader like? What's the environment like? And how can we attack it? So I'm not a big mobile guy. I like a lot of different things. Drew is, you might have seen us talk at Android. And so this is where I pulled him in to really look at this process. So I'm going to let him talk about this portion of the Jolla.
Cool. All right, thanks. So like Vitaly mentioned, like we wanted to figure out this device, and the first thing we look at is like, how does it work? Like, what's the surface? So we need to understand the image type, how it boots. We need to understand the device topology, and then again, we're kind of after like what's in the RAM disk, because that teaches us a lot about how a device works. So the first thing we look at is the topology. This can be done within Sailfish. You know, you look at the output of mount, you look at the output of proc partitions. A lot of devices, you can look at the block devices under dev block platform and then the name of the SOC. If you're lucky, they've left you a by name, which they did in this case, which is very handy for helping you map out what's what. And then once again, we want the RAM disk contents here. So here's a rendering of all the partitions on the phone here. You can see the by name is on this column here, and this points to this physical block device partition. And so we can learn a lot about how the phone is laid out just by looking at something like this. So we know where the recovery is, we know where Sailfish lives, we know where like the secondary bootloaders live and stuff like that. So that's very helpful to see. And then I usually put together something like this. This is the output of proc partitions with an added column that I added of like, here's what we know, this is a good thing to do to map out, just so you know, okay, this is the partition, this is what it's for. Just keep stuff in mind. And then it's, we're usually after the boot images, right? So like just to learn about how the boot process works. So we look for good candidates on what might be that. So, you can see here on 20 and 21, I've marked, this looks like a good candidate because it's 12 megabytes. It seems about the right size. So let's investigate these first. And as it turns out, one of those was actually the recovery, and that was partition 21. So we need to get the images off the device. Luckily, Jolla has a pretty good, it ships with root. If you want to enable it, you can enable developer mode. So we have root already. We can just dump these partitions off the phone. So this is an example of how you would do that. We wanted partition 21 because that's where the recovery lives, but this would work for any partition you want to investigate. And I usually just dump all of them and investigate them that way. But I'll show you some tools to help explore and extract that. So what we thought was very interesting was that this phone actually uses an Android boot image, which was lucky for me because I know quite a bit about that. So you can see here the Android boot header and the kernel command line. We know this is the recovery because they're passing the recovery. All sorts of parameters here. So like this is good. We found what we're after. So now how do we investigate that? There's a few tools for that. Binwalk is a good one. This is just an example of like me exploding out and extracting the contents of this image with binwalk here. This is the recovery itself, so you can see how it's made up on the different components. We can also use a tool called MakeBoot, which is a little bit more friendly and happens to work with this image type perfectly. Sorry, that's kind of hard to read, but this is the layout of the partition in question. We have all the things we need. And now we can see the exploded out RAM disk at the bottom. So that's awesome. That's what we want to see. We want to investigate that more. So we'll talk now a little bit about the boot and recovery structure of this phone, and then how to inspect this firmware, and then we're going to look at how the lock and unlock process works for this phone, for the bootloader and other features like that. So the structure, as I mentioned, this is an Android-style boot image. It has the Android boot header. You've got your compiled Z image, and your RAM disk, the rootfs CPIO. So perfect, we have everything we need here. Just a little bit on image signing. They do not enforce image signing on this device. This is something that this is a response from the Jolla dev team that probably not on this hardware, but this is something we're interested in doing in the future. So this is going to add some additional security to the device when they do this. There are some little kernel bugs in this bootloader that were patched in the latest release. So that's good to see, like, that they're proactive about that kind of stuff, but we still don't have image signing, so that's not great. So recovery fastboot mode. In order to get into recovery on this device, it's a volume down and power without any USB connected. You have a telnet-based connection, and it's basically like a weird menu system of a series of shell scripts that run this instead of an actual binary, like you would usually see in Android. And fastboot is similar, except that you do plug in with USB, and you need to use the specific fastboot identifier in order to talk to it. They've pretty much stripped out most of the arguments that fastboot supports on this, so you're not going to get a lot of cool features out of that, and it's locked by default, but so it goes. So here's a picture of the recovery menu system, and you can see you can get a shell, you can do a factory reset, you can lock and unlock the bootloader from this menu, which is another interesting difference that most Android phones, you can't control bootloader status from recovery. But and you can see here we've gotten a shell, over root shell on this device. So I mentioned the recovery menu is driven by shell scripts, contains options to lock, unlock, that sort of thing. It can be protected by setting a PIN code within the device itself, which we highly recommend you do, because you can get a root shell pretty easily otherwise. Some interesting quirks with this. They claim in the documentation that after 5 attempts that you have to wait 24 hours. We know this is nonsensical because it's a read-only RAM disk. So essentially what they do is they touch a file. The unlock code looks for the presence of that file and then says, no, you can't try anymore. Not surprisingly, a reboot clears this file because there's no way for that to be persistent. But it does effectively slow down your attempts to brute force this pin because you get 5 tries and then you have to go through the pain of a reboot and getting back into the mode, replugging the cable, etc. So we wanted to figure out how they're protecting these modes. So I mentioned the security code can be set via userland in the system settings menu. We discovered a standalone binary called restore lock in the recovery RAM disk when we extracted it. And then there's some interesting interactions with other partitions on this device. So Partition 27, which is labeled the security partition by the device, has a header that shows the lock and unlock status of the device at any given time. And we found what looked like a possible hash. So like, okay, that's interesting. Let's put that aside and come back to it when we learn more about it. We also saw that partition 6 changes as well based on whether the bootloader is locked or unlocked. And that partition 2 had some interesting strings inside of it that looked like they might be part of something bigger. So again, we investigated that, wrote them down. And so here's a look at the partition 27. The first few characters, BBBC, means that this phone is locked. If those characters are not present, that means you've unlocked the device. And then after those first 4 characters, we see this interesting hash. We're like, wonder what this is. Maybe there's something cool here, so let's keep note of that. Then we're going to look at partition 6 here. This bolded string appears when the phone has been unlocked. This string is not present otherwise. So interesting thing. So when we start looking at these partitions, it's a good idea to get a map of them before you do anything, make a change, and then reinvestigate everything and see, oh, look, something changed. Now we know a little bit more about how it works, and then we can follow up more on those things. So other images, I mentioned partition 2. We see this string here. This ended up being a device UID, which Vitaly is going to talk more about later. But something that's like, cool, this wasn't here before, so let's see that more. So some thoughts on the boot process for this phone. If you have a Jolla, definitely enable the device lock and developer mode, because otherwise you have very little security, especially if somebody gets one of these phones from you. This is clearly not an ideal security model whatsoever, but it's at least something, so like worth doing if you have one. And we just kind of think that this is an interesting mix of very different software that seems mashed together, so it really increases the attack surface potentially for other issues that might come out later. So learning everything we did from that, Vitaly and I were able to sort of put that together and investigate this a little further, but I will pass that back to Vitaly to talk about how we did that.
Cool. Yeah, so, we had some of this research before this con, and kind of for this, we wanted to see how can we put a lot of this knowledge that we gained, put it together, and actually come out with either an attack or a bigger understanding of the phone. So we wanted to say, okay, so we know that we saw all these different values that we just showed. We know that the phone has to store the lock pin somewhere, and we want to see, well, how does it store it, and can we recover it? So, we saw that hash that you saw earlier that Drew was showing you, and it's 160 bits. So if you don't work with this kind of stuff a lot, and you're wondering, okay, what kind of crypto, what kind of hash function was used for this hash, the size of it, the character size, is a pretty good way of determining what it could be. A lot of things are similar, but at 160 bits, it's a pretty good bet that it is SHA-1. So we said, okay, it's probably a SHA-1 hash of some sort. And we saw that restore lock binary, and it does what we want to investigate, right? It locks and unlocks the bootloader, and it has a function that can check the pin. So I don't know if I mentioned this, but this pin is actually used for the lock screen on the phone, to protect the root shell in the bootloader, and to guard against dangerous functions in the bootloader itself. So that's why we had some interest in it. So anyway, we thought this restore lock binary, it does what we need. Why don't we start with that? So just real quick here, we started looking at an IDA. I know it's hard to reach, is this assembly on the screen, and I'm not a great reverser by any means. You could see though that there is kind of a static string up there. There's another one further down, and then you could see it starts digging at partition 2 and putting a value together, right? And we're like, what is it doing here? And then past this, you see a call into a function called EVP SHA-1, which is an OpenSSL function. And then HMAC, you see that at the bottom there. So we thought, okay, it's actually HMAC SHA-1 something. Now, yeah, so it's putting this string together. It's grabbing something from this block partition, static string, another thing from partition 2, and then another static string, and it's setting up SHA-1. So we figured just by the disassembly and intuition that this must be the key for HMAC SHA-1. So now we said, well, how do we extract this key without really trying to go through this process and reassembling what it's doing from the disassembly? So I was thinking, okay, restore lock, it lives in the recovery, which is its own little operating system. Maybe we need to instrument that with tools. And Drew said, well, it's an RML binary, regular binary. The partition layout is the same in the operating system as Sailfish itself. And Sailfish has a ton of different tools that you can use. GDB is available. All the tools that you're kind of used to for this kind of work are available or available from a package manager. So we thought, why don't we try and run restore lock in the operating system? And it worked. You could see here, this is it running. It was a little quirky at first because you can see it doesn't give any output, but what it does is it sets a return code. So you might know in Bash, the return code is always stored in $? So you could see the wrong code, and of course the right code is 31337, and it returns a 0 saying this is in fact the right code. So now that we could see it working, we thought, okay, why don't we just have restore lock tell us what the key is, right? So idea was, why don't we run a store lock, run in GDB, that's available, it's a debugger, and we'll set a breakpoint and then HMAC function, which should actually have the key, it needs to use it, and then we'll grab the key when the breakpoint hits. So to do this, we needed to take a look at like what is the prototype for this HMAC function? And it's an OpenSSL doc, so it's the regular function. And you could see the second argument passed to this function is a pointer to that key that we want. So I was going to do a live demo, but I don't think there's a ton of time, so I'll just tell you, for anyone that's new to reversing like myself, if you know ARM calling convention, there is an ARM chip in here. Arguments are passed into registers up until it exhausts a certain amount of registers. So the first argument, this EVP MD thing, would be in register R0, and means the second one would be in register R1. So we hit the breakpoint, you just said BR, it hits the breakpoint for HMAC, and we said, okay, we're at the breakpoint, it should be the second argument. We can use the examine command, which is X in a GDB, and then it's probably a null delimited string, right? It makes sense the key would be stored as a string, so you could pass / and a modifier, say S for the string. And like we said, R1 was probably the register that would actually hold the value. So $ says, we're going to be looking at a register, and then R1. And you could see this is the memory location, and then we have this really interesting string. And we thought, this is probably the key. But how can we test that? We have the hash, we have the key. Can we re-encrypt our own PIN and get that same hash back? So there's a ton of ways to do this. I just wrote a few lines of Ruby because Ruby is my go-to for just quick scripts. And wrote something like this. It just takes the PIN as the command line argument. It already has that key in there. And it worked. It was the same hash. So from this, we weren't quite sure what some of these numbers that were being used, but we saw the process for how to extract the key, how it works. And the last thing to do would be like, how do you actually go from this to actually extract the plaintext, the actual PIN from the hash, knowing the key. I don't have a screenshot of this, but Hashcat did a really good job on this very laptop. It took like a minute to recover the key. It's a numeric PIN. I mean, and it's SHA-1 with 1 round. It's not going to take very long to crack, so that worked. So, I mean, that's just a little bit of an insight into the bootloader and some of the protections and, how we go about like exploiting things like that. So bootloader, very interesting attack surface on any mobile device you come up with. Doesn't have to be Jolla, it could be Android or anything. So the next layer would be the operating system. And the one thing you find is mobile operating systems are good for looking for bugs, even if you're not like at a very advanced level. Again, I don't do a ton of like overflows or anything, but you know what? The bugs from the 90s, they're alive in early versions of these operating systems. You see Android, a lot of the early Android releases, even now, are being rooted with just some of these bugs that you thought died in new systems in like the mid-90s, right? So, of course, you also have Linux, you have userland, any bug that comes out from Linux kernel is going to affect it, but we were more interested in things that are specific to the phone. So, real quick, there's a lot of interesting binaries in the device. There's a QSACOMD that's used to communicate with Trust Zone. It's a Qualcomm binary. There's a lot of attack surface. We're going to skim over it for this talk. The attack surface appears small, but then you look at it, there's almost no listening services. There's DHCP, but that's about it. So we're really looking at the local attack surface. Real quick, we also just looked at memory protections that are inherent to the phone. The compiler, SC compiler, can set a lot of protections to make exploitation a lot harder. REL, PI, SLR, and they're applied, but there's not a ton of them. There's no kernel hardening or anything like that. This is another thing that if you want more explanation, check out our Echo Party talk. Chris did a lot of talking about this. So. Then XBit support is not supported either. It's an ARM feature that disables execution on the stack. Stack and errors are all pie, not that prevalent either. I'll point out for this script I didn't know about, there's a thing out there called checksuck.sh. So if you want to figure out, does my Linux binary have all these compiler protections, check out checksuck. It just uses readelf, which is a very standard binary you find in Linux systems, to look up all these protections. So if there's any takeaway you get here is that the script is pretty cool at quickly figuring out what the binary has. Anyway, the application layer real quick, it's written in C, C++, so you might imagine there's a lot of memory issues in some of the apps, even the third-party apps are C++. Qt, which I was not very familiar with coming into this, as you'll see, is being used. There's QML, which is like a markup language they use. It looks like this. I'm not even going to touch it, but this is the kind of thing that you need to write the apps. So, the userland. You log in as Nemo, and pretty much everything runs as Nemo. There's a whole like nautical theme to this phone, so they go along with it. You access the phone with Nemo, everything runs as Nemo. This is changing in the new version of the OS. But as you could probably imagine, running everything as one user is not a great idea. But we wanted to figure out what is its local attack surface. Now the second thing you see, finding SUID binaries, this is a very standard thing you would do on any Linux box. When you get on a Linux box, you want to figure out what can I attack, how can I gain root. This is a great command to run. For anyone maybe less familiar with Linux, this is SUID means if it will not drop its privileges. So if it's owned by root and I execute as a regular user and I have some sort of exploit in it, chances are the code will run as root or whatever it's owned by. But the Jolla actually has a bunch of other interesting things. It has this thing called invoker, which will actually run binaries as other users, even though they're not SUID. And that's really interesting because you can get tripped up thinking, okay, this is my whole attack surface, but there's this whole other mechanism that's in there. So. A bunch of interesting binaries that are on there. There's SimKit. We're just kind of looking into it. It's a group SGID. CSD is really interesting. It runs this like diagnostic menu. If you have a Jolla, you can type that code into your phone dialer and it'll pop up a diagnostic menu. And it's neat by itself, but it's also SUID root, so it's ripe for attack, so we thought. Booster Silica Qt5. This is part of this whole invoker map launcher D thing. It launches Qt5, sets up the right environment, and potentially crosses access boundaries. And then Devil Sue is their own custom version of SU that gives you legitimate root on the phone using your own password. It's kind of like sudo and Sue combined. It's nice because it's written in C. No stack and errors, no pi in it, but we don't have any exploits there. So. Okay, so what to do? I mean, you have all your tools that you're used to in Linux. You have your GDB, your readelf, so you can use that. It's always good to fuzz input, fuzz environmental variables. That's a good way of like kind of shaking things out of a binary first. We did not have a ton of success with this actually here. So we thought, okay, let's look for low-hanging fruit. And one thing that we thought about is it's really dangerous for SUID binaries to shell out. If they're calling a shell, it's really hard for a binary to do this securely. Two common calls whenever I look at this are system and popen, because they always invoke a shell, right? So I'm like looking at these, and I'm using readelf. You can see I'm just grepping through it, and I'm like, man, none of these have system or popen. I'm screwed. Nothing's even invoking a process. And this is when I realized I didn't know much about Qt. You know, I think Qt, oh, it's drawing windows, it's a nice GUI set. But no, Qt has like its own string classes, and it has its own class for running processes. And that's called QProcess. And as you can see, CSD, in fact, calls QProcess to run something else. So I was looking at it a bit. I know this is a terrible screenshot, I'm sorry. And you could see that it's running QProcess within CSD. And I just wanted to get a quick idea of like, where is this happening? You can see the function call, it's called SD card path. So I thought maybe in this diag menu that you can bring up, there's something that works with SD card path. So I started looking into it, and I realized, I think this is in the other one. Yeah, right here, you could see it right here, it's running grep. And it's running grep without a full file path, meaning it will probably run it from like the directory that you're currently in if you convince it to. So I'm like, awesome, it's SUID root, I can get it to run grep, but really it's going to be something I design, something like this, that just sets UID, throws a UID in a file, and I'm going to see root, and it's going to be a cool root exploit. And it looked promising. I ran it. I set the path to first check out like the local directory I'm in. I had that binary you just saw called grep in there. And you could see it kind of fails here. There is no, it's supposed to grep out your UID and it's not there. So it really is, I'm really affecting the flow of the application. Yeah, unfortunately it didn't work. The flag file had my own UID. Why? It drops privileges. This is the kind of thing that happens. And there's also something called privilege mode in bash. So if the original process doesn't invoke bash with -p, bash will also drop privileges when it's being called, unless you're in a Debian system, because they took this out to support UUCP. You remember UUCP from like the 80s? Debian like took out security measures from bash to support it still. Anyway. So we found out basically, if you look at it in the disassembly, there are like 2 branches. There's like do all this stuff, dropping privileges, and then keep privileges for like 2 things. Pretty much all you can really do with the privilege operations, like disable the charger. This is like some of the stuff it does with sys. This is really the only stuff it does when it doesn't drop privileges. So it was a bit of a fail, but it was an interesting exercise, and it shows you how you might be able to attack a binary. Fuzzing didn't get us very far. We got some weird things, but no real exploitable crashes yet, so I'm not going to spend too much time on it. But there's other low-hanging fruit, and this is new. I just got done talking to Jolla about this, so we talk about it. Init script. Android, a lot of like Android bugs come from init script, and I knew that there would be some interesting things here. So if you grep init and you look for like chaon and chmod, you can get some interesting things that are happening. Because if you can get it to change the user or change the permissions in a file that you own or where you can place a symlink, maybe you can get it to affect something else in the device. And an interesting thing here is actually symlinks did not work. I don't know why. I don't know if this is like a protection. Hard links work though, so okay. Once we figured that out, we managed to come up with a few fun examples. This one's not fixed yet, so I redacted the name of the log. You guys can figure this out if you haven't, but I redacted it to be nice. It is fixed next release. They knew about it themselves. Kudos where kudos are due. So you can see right here, we have Etsy Shadow with no permissions. Regular user cannot read it, as it should be, right? Because that's got the keys to the kingdom. Then we do a hard link to Etsy Shadow, this vulnerable log. You could see the hard link is created. Now it's basically just the same as Shadow. Then we trigger whatever action causes this log to happen. It's a certain action you do on the phone. And then now you could see, and what's happening in the background, I should have had this line, it does a chmod 644. But since we had a hard link from the log to Etsy Shadow, now 644 has been applied to Etsy Shadow. And is the 666, thank you. Drew knows Unix. And you could see I have read write. I can dump the constant of Etsy Shadow. I can add a passwordless user, and I can root the phone. And in fact, this worked. So there's a bunch of others that just gave us read. This is just a good example, and a good example of the kind of thing you could look for on your phone. Another fun example that has already been fixed, I could just show you. They made a little mistake. When you plug the phone to USB, it's like, okay, I should give an IP address because USB can be used as a network. It uses UDHCPD. Unfortunately, they reconfigured it to put the config file in /temp. So I just symlinked it to Etsy any file. Shouldn't be able to write to Etsy, right, as a regular user. And then I plugged the USB cable into the phone, and boom, as soon as that happened, I looked and any file was created. And the contents of it were the contents of what the DHCP server was throwing in there. I wasn't able to control the contents, but even if you get a few characters in there, init scripts, bash scripts, they're very forgiving. They'll go through all the garbage, and then they'll execute any commands you have in there anyway. So even if I could have controlled one value, maybe one of these IP addresses, I could have probably clobbered an init file and gained root that way. They did fix this, though, so this is good for them. And then they figured this out themselves. This is just good. So a few kind of low-hanging fruit, but it shows you what kind of things are available on mobile phones. Okay. Just real quick, when we were first doing this research, shell shocking is new. We want to talk about it. It was vulnerable, but we couldn't really find any exploit vectors. Didn't have a lot of remote services. Was not using DH client either, so there was no remote vectors that we can find. Maybe we missed some opportunities, but yeah, weren't sure. The kernel, always a good thing to look at. 2 lessons we learned. Yeah, look at the version, look at the modules that are loaded, but don't assume. Because this kernel version supposedly was vulnerable to sock diag. Sock diag was how a lot of Android phones were being rooted, Linux boxes were being rooted, so I'm like, okay, this thing's vulnerable. Now, I didn't have ARM exploit code, but I looked in the Android Hacker's Handbook, which is an awesome book, by the way, and they had sample code that just triggered a kernel panic. This bug basically was an out-of-bounds array write. So you could like specify a really huge value to this array, and it would crash the kernel, panic the kernel. So I wrote a little tool to test that, and I just wrote a loop that would hopefully just blow this array out of the water, and it didn't work because they port patches back to the kernel without bumping the version. I mean, you see this on Red Hat, you see this on other systems. So it's a good thing to remember that just because the version says one thing, it doesn't necessarily mean that that software is vulnerable to what the CV says. The other thing that we learned is the opposite is also true. Don't assume that because it's like the Linux kernel, it's going to be secured like every other Linux kernel you see out there. Like a good example is this proc sysrq trigger, procfs endpoint. It exists in every Linux box, but a regular user cannot access it. They cannot write to it because it simulates pressing the sysrq button. But because Jolla is very loose with permissions and you're in the system group as a regular user, you can write to it. And you can, for example, write B to it and it'll reboot the phone as a regular user. So just because it exists in every other Linux kernel doesn't mean it's secured as well on the device that you're looking at. Apps can trigger it, yeah. And, anyone can trigger it. So there's a lot of interesting attack surfaces like that to map out. The next thing, IPC. Processes, they have to talk to each other, right? And we found this is especially prevalent on mobile devices, this is kind of ripe for vulnerabilities. iOS is a very secure operating system, but it uses URL handlers for IPC, which seems a little messy. There have been vulnerabilities associated with that. Android uses this whole intense binder system. It's also got ashmem, which is shared memory. There have been vulnerabilities in the past related to that, or they can affect apps in unexpected ways. So what does Sailfish use? dbus. I don't know if you guys are familiar with dbus. It's free desktop, like the GNOME people. It's their system. You see this a lot in Linux components, and they really adopted this and use it as their own. Common to Linux environments. Everything runs as Nemo, which is not a good thing when you have like an IPC mechanism like this. They have dbus monitor. It comes with the phone. It basically acts as a dbus sniffer. You probably have it in your Linux boxes too. And to show you how bad this is, that like everything runs as one user, and you have the sniffer. A regular user, he was not a security person, discovered, I'll show you. He posted this message to their message board. He's saying, hey, I was playing around with dbus sniffer or dbus monitor, and I saw my Outlook password going around as a regular user, meaning any app can just monitor dbus and pick it up. And so they changed this model, and now you see a lot more information, but shows what happens when you use just one user for everything. We wanted to push this a little further. Tavis Ormandy from Google released a tool called dbus map and map for dbus very recently, like just a month ago. I was like, thank you. This helps me a lot. It helps you enumerate the methods and properties exposed by dbus. He found a cool exploit in Debian using its USB dbus endpoint. So take a look at that for how dbus is exploited. So we saw a lot of standard dbus services. We also saw a lot that were like Jolla specific. We wanted to focus on that. Kind of research is ongoing into that, but I'll show you a little bit. The cool thing about dbus, well, for us, is it can affect code across privilege boundaries, right? It can be running as root, but you might be able to send a command to it via dbus, and then you're affecting it somehow. So the same vulns can apply, like command execution, memory corruption, etc. We did some manual fuzzing. I'm looking into dbus fuzzers. If anyone knows of a good one, let me know. But there is dbus send, which also comes with the phone, and it lets you interact with dbus. And here's a quick example. This is something that was actually found by dbus map. It says this is a method. It's called this. And you can plug it into dbus send directly. You want to use print reply so you could see how it replies. System means use the system bus because there's also a session bus in dbus. And then the rest is self-explanatory, right? It's got the destination and everything you see there, and then the actual method that we're going to call. And when I call this device UID method, it came up with a string, which you might remember from back when we looked at the bootloader. This is the first part of the key that it uses to encrypt your PIN. So it is a device UID. It is different per every phone, but you can grab it as a regular user using dbus very easily. So that's a way you can interact with dbus. You can also set properties, and that's how you might be able to fuzz some of the actions. User interaction is another interesting thing. How can you attack the user? So anytime the user opens a file, they're open for attack. Any exposed services, which is not a ton here. Not a ton of attack surface here, but one thing we did look at is the contacts. You can import contacts. You can import VCF files. I used a Ruby gem called vcardigan to generate a ton of valid VCF files, a ton of fuzz strings. I got a lot of hangs, but no crashes yet, unfortunately. But that's another interesting attack surface in the phone is like, what does the user open? How can you get the user to open something that could be malicious? Third-party apps, they've been working on this. They have a QA process now for third-party apps, but of course, anytime you have kind of a rich app environment, there could be issues. Another thing we want to look at real quick is like, how do you assess the platform itself? If you're tasked, if someone said, look at a Jolla app for us. Okay, for iOS, for Android, there's a lot of guides out there. How do you proxy traffic? How do you look at things like that? We looked, and it's not, you want to be able to set up a proxy. You want to be able to create IP tables rules. Luckily, a lot of this is available for you. It's such an open system that you can do this pretty easily. Here are the tips. I mean, you have to set the proxy in several files for the browser. You have to do it in a JavaScript file. Otherwise, there is actually an option to do it for the rest of the things. Jolla is smart. They cert pinned it, which means like it will only honor their cert. So even if you throw your own cert in the trust chain, let's say you're using Burp, and you want to look at traffic, and you go through these steps of actually adding the CA cert from Burp to the trust chain, some things will work, but things like the store will not work, because it is using certificate pinning, which is a great thing to do in mobile apps, because it says, yeah, it's trusted in my trust chain, but this is not Jolla certificate. We don't use Portswig or CA. We use Digitrust or something, and it will drop the connection. So that's good, and that's something that I think a lot more mobile apps should do, because mobile apps only connect to one endpoint, and you can predict what the CA should be, so you don't have to honor the rest of the trust chain. Yeah, please. Here, it was just a case of when we put things into the trust chain and we could see certain traffic and certain things would not work. You could go past it. You could start kind of reversing and seeing if some of the code is present. Pretty prevalent in iOS. Our coworker Daniel Mayer did a lot of research into actually cracking, kind of like patching out certificate pinning within iOS apps, right?
Yeah, there's a great article on our site by Daniel that explains, like, if you run into cert pinning, here's how you could get around it in certain cases. So definitely check that out.
Yeah, there's iOS kill switch. So for different platforms, there's ways to do it. Here, if you run into it and you really want to get around it, you would have to patch the app and you'd have to knock it out or something. But yeah, if you see that you're sure that everything in the trust chain, it just won't connect, that's a pretty good bet that you're cert pinned. That's a great thing to do. I'm all for it. We cover this. Just to note that all your old friends are here for looking at apps, GDB, LDDS trace, strings. These are great tools for looking at a binary in any Linux box, mobile phone, and they're all available here. QML and Qt, it's something to look at, I guess, as far as sources go. This we kind of talked about. I shouldn't move the slide, honestly. I forgot to. But Invoker, like I said, is something that's used to start apps, to save device memory, to launch apps in the right environment. And it's a wrapper for this Map Launcher D. So this is an interesting thing to research on this phone, because oftentimes it'll actually launch it as a different user and such. Not something to expect. Hardware. Hardware is an emerging attack surface. It's very interesting. There's a lot of classes on it now. There's a lot of tools coming out to play with it. You have JTAG tools. You have logic analyzers that have really intuitive software. They'll let you play with this kind of stuff. They'll detect the protocol. It can often be used to bypass software restrictions. It's something that Chris Whedon, our other researcher, did a lot of work on. So again, check out his slides. We're not going to talk about it too much, but he gives you some ideas of things that you can do. There's a ton of other presentations, like classes. Man, at Echo Party, we saw someone to bypass restrictions on a processor using a camera flash. So it's a whole new world, and it's a really interesting world, and it lets you bypass a lot of the restrictions that are even in the kernel and things like that. So I'll mention real quick that the other half, that smart cover, it's got NFC, an NFC sticker. I'm sure in time soon. Oops. I'm gonna grab the Jolla here real quick and show you. Oh yeah, I got time. See, this talk was long when I practiced it, and that's a little short, so I have time to grab it and show you guys. This is the box that the Jolla comes in. Like, if you're a hacker, this is cool when you get it, because right away you see all this text on here. This is all like C++ and Qt, so right away you're like, oh, this is a cool thing. They're kind of going for the technologically minded person. I should say, actually, this is a finished phone. I forgot to add this. I'm going to jump back a little bit to say, this phone, it's Finnish, but it's available in certain countries like India and Kazakhstan. But an interesting thing that happened about a month ago is the Russian government said, hey, iOS and Android have like 98% of our market. We don't like that. So they started talking to other manufacturers. And Jolla, they actually had a sit down with, and they're talking about creating a new version of the Jolla that won't have Facebook, it won't have Twitter, but it'll have all your Russian government-approved apps on there. And it's going to be kind of like the national OS of Russia. So this phone might become a lot more interesting soon. But yeah, but to get back to what we're talking about, this other half, it's this thing. This is the one that comes with it. It's just a plastic cover. But you can see there's an NFC sticker here. It's hard to see, it's white. This NFC sticker is what tells the phone, it has a UID on it, and it tells it download a certain ambiance and a certain theme from the store. So obviously an interesting attack surface. And then it supports things like the keyboard and other things. There's pins on here. And these pins use the ITC serial protocol. And if you check out Chris's research, you'll see him actually hooking up to it and trying to fuzz it and being really frustrated because the NFC radio and the ITC radio only turn on for a second when a switch is pressed in here when you put in the cover, and then it turns off. So you have to literally be like, press, fuzz, you know? You need to build a servo or something to do this.
Use like a toothpick.
Yeah, using a toothpick.
Just like over and over and over.
But the NFC is interesting. The sticker is standard MyFair Ultralight. You see these a lot like one-time passes for transit systems. You can read them using your Android phone, as I'll show you. It's got a daemon that handles it called the other half daemon, TOHD. The NFC stack in the N9, the kind of the spiritual predecessors, was fuzzed by Charlie Miller. It's the only one he had no results in. Might be different in Sailfish, though, so another interesting attack surface. For those of you that know a little bit about NFC, this is just NFC tag info. It's a free app you can grab from the Android Play Store. And if you read this tag, this is how it's laid out. So they did lock the first two sections, and the page 2 is partially writable. I don't work a ton with NFC, but if you do, pull me over and we can talk about this. This is actually one of Chris's slides about the ITC port. There's a developer kit you can use, and you can use some of these tools I was saying are coming out. Bus Pirate is a great way of interacting with some of these things. Logic Analyzer. There's some cheap logic analyzers with great software out there now. Put in developer mode, use GDB, use Python that's on there, and you can interact with this pin. The community for this phone is really great, and so you'd think, oh, ITC, it's esoteric, how am I going to attack this? And you Google, and people have breakout, like the people did breakout boards for ITC, people have whole schematics. Like people are really involved with this phone, and so there's a whole community to pull from for resources for this kind of stuff. So yeah, that's the hardware side. We glossed over it, but there's some cool stuff you can do with that as well. So. Just real quick, we want to say thanks to Chris Whedon. I don't know if you all see this, but he's not here. And check out our Echo Party deck for his hardware stuff. He does a lot of great stuff. He's a smart dude. CircleCityCon, we're really glad to be here. It's really cool to be able to present some of the updates for research. Thank you everyone that came here on a Sunday to hear about an obscure Finnish phone. I appreciate it. I appreciate you listening. And yeah, does anyone have any questions or any comments or anything that I might have said wrong that offended your technical knowledge? Anyone? Here's the Jolla. Oh, here's Sailfish. Very nautical. I wish I had the name of what the new release is called. It's hilarious if you don't speak Finnish. Sailfish, OS. Oh, I'm not on the internet, sorry, I turned it off. It's great. It's this like Finnish name that looks like it's maybe like UTF characters that aren't rendering properly, but no, it's a proper Finnish word. I love the Finns. Their language is awesome. No questions? Nothing?
Thanks,
Thanks for coming, everyone. Appreciate it.